Jean-Francois Lebrec. Jean-Francois first got involved in space activities starting in 2008 when we had his first of 3 internships at the Canadian Space Agency. He completed his bachelor's degree in Montreal in 2010 and went on to complete a master's at the EPFL in Switzerland with a focus on space technologies. During that time, he was involved with several projects at the Swiss Space Center and the European Space Agency, and spent 6 months in Moscow completing his master's project on the attitude determination and control system of a satellite for the observation of exoplanets. After completing his master's degree, he went on to work for MDA Corporation. During his 8 years with the satellite systems provider, he worked as a thermal and structural analyst and was also involved in the manufacturing and design aspects of the business. In 2020, he was hired by Maya HTT as a senior structural and thermal analyst, where he's currently providing consulting services for the space industry. Welcome, Jean-Francois.
Thank you, Bill. And, good job on the pronunciation of the French name. Very well.
Thank you.
Good day, everyone, and thank you for being here with us today. In this session, we're going to discuss a project that we've completed recently for lunar exploration, we being Canadensis and Maya HTT with the support of the CSA and Alatherm. So, everybody that's present in this channel here today is probably aware that lunar exploration has made a comeback to the limelight in the recent years. In fact, in 2019, the US government issued a new directive to have boots on the moon by 2024, which is coming up pretty fast. So it's no surprise that there's a big international effort towards that objective. Now, when it comes to space and lunar exploration, Canada isn't standing on the sidelines. The Canadian Space Agency has been preparing to support the international effort to go back to the moon for more than a decade now. And in 2019, they launched the Lunar Exploration Accelerator Program, or LEAP, to foster innovation in the areas of strength of the Canadian space industry, such as AI, robotics, science, and health. And it's with that objective in mind that the MERIT project was created. So MERIT, or Mobility and Environmental Rover Integrated Technology, it's a project whose objective is to close strategic knowledge gaps in some areas of the lunar exploration, namely the rover, thermal control, and mobility. Although the technology we've developed within this project isn't currently scheduled for a launch, the project itself was not limited to the design phase. So we also went ahead and built and tested a prototype to verify the feasibility and performance of our system. The MERIT project was divided in 2 parts, one for the drivetrain assembly, or the locomotion system, and another one for the rover body that we call TREE for thermally regulated electronics enclosure. This presentation today is going to focus only on the TREE because I only have 20 minutes. The objective of the TREE as defined in the mission plan was to design and build a system that's able to survive the 14 days lunar nights without a radioactive heat source, which most of the lunar rovers currently have. It obviously also needs to survive the equally long lunar days with the maximum power dissipation to achieve as many scientific missions as possible. So in a nutshell, what we're trying to do is to develop a solely solar-powered lunar rover. In order to develop and advance a design, we needed more specific information with regards to the rover and the mission. Just going to the moon is not complicated enough. So what we did for MERIT is we used a phaser rover, which is currently being developed by CSA. That rover is the Canadian contribution, or one of the contributions to a joint mission between the CSA, ESA, and JAXA to send a rover to the moon using the Lunar Gateway as a staging point. It's a Heracles mission. That mission calls for a medium-sized rover in the 300 kilos range, or 700 pounds. Its life expectancy is of 1 year, so about 13 lunar days and nights, and it will need to travel a distance of at least 400 kilometers. Its dimensions are about 80 inches per 60 inches per 45 inches, and it contains a number of scientific payloads. One of the main objectives of this mission is to collect samples, rock and soil from both the sunlit and the permanently shadowed regions of the moon. And finally, it's an exclusively solar-powered system, which is the main interest here. Now, what we did for the tree is we essentially built a fully functional spacecraft to represent the rover body. It has an onboard computer, power conditioning and distribution unit, batteries, motor drive amplifiers for the locomotion system, an inertial measurements unit, camera, and a fully functional drivetrain. For the thermal design, it was an interesting challenge here. To survive the lunar nights without a radioactive heat source, what you need to do essentially is to minimize the heat leak to the radiators during the night. But you still need those radiators to be as big and as efficient as possible during the day to dissipate the heat. And also another constraint is you can't have too many radiators because a lot of the real estate on the outside of the rover is needed for the solar cells to charge the batteries and operate. So in order to meet all of the thermal requirements, we converge on a design that has the different internal avionics and separate thermally regulated enclosures within the rover body. For the design, we're making use of existing and well-known technologies such as MLI, multi-layer insulation, thermally insulating standoff, and heaters, although this is a passive session. And in order to address that night versus day challenge, we're also using a new type of LHP, of loop heat pipe, which was developed by Alatherm in Latvia. What's special about this LHP is it uses a passive valve switching technology to control whether it's operational or not. So basically, you can have can let the heat through during the day and completely close it down overnight. Keep the heat in. And it also has a modular design, so it's easy to take each LHP apart and assemble them and adjust them for the specific applications within one same system. By playing with the different parameters of that thermal design, we managed to reach a solution that seemingly achieves all the objectives. I don't want to sell the punch just yet. Now, since manufacturing is in the topic of this presentation, I'm just going to skip ahead and go to the testing phase. Well, once we design and build the system, we performed a TVAC test to verify the real performance. We did the test at the David Florida laboratory in Ottawa, and the test lasted about 12 days, which is a bit short of a complete lunar day and night. We had an environment temperature closer to the temperature on the moon. We flooded the shroud with liquid nitrogen, which got us down to about minus 200 degrees, so warmer than that. We also installed heaters on the inner side of the radiators to simulate the heat load from the sun. For this test, we could have used dummy masses to represent the internal components, but we decided to go ahead and use the real components as we felt like this would give us a better understanding of how the system works as a whole. During the test, we performed several cases under vacuum to try and simulate the real operational scenarios on the moon. So we did a hot operational steady state with full solar loading, solar array circuits operational, and maximum internal dissipations. We also did cold operational, cold standby with minimum internal dissipations. And finally, we did the lunar night survival phase with practically no heat dissipation and the thermostatic heaters activated. That last part was the longest portion of the test. It lasted almost 5 days. So, as I just mentioned, the test lasted 12 days, which is shorter than a full lunar day. The ideal scenario here would have been to do a 28 long days TVAC test, or even more if possible, but that's not really possible within the time and cost constraints of a normal project. Therefore, in order to bring confidence to the values we obtained during the test, what we did is we performed a thermal model correlation. The main objective here was to confirm that we had enough power to feed the heater lines over the full lunar night. So we used the thermal model that we had developed for that. So we developed the model using SimCenter 3D Space System Thermal. The structure, the electronics, the MLI, and the radiators were all modeled explicitly. For the thermal insulating washers, we modeled them using a temperature-dependent thermal coupling because we were aware that there was a slight temperature dependence, variation over temperature. For the LHPs, we modeled them using a temperature dependency to account for the passive thermostatic switch. So it had a non-temperature, enough temperature, and a transition phase between the two. And since we had temperature-dependent values, we performed the correlation using two different data sets, one for the cold part of the test and one for the hot part. So we started off with the cold plateau correlation, which is representative of the lunar night survival. What we did during the test is we allowed the system to to settle for about 4 days with the heaters. And then at the end of that lunar survival phase, we turned off the thermostatic heaters and we replaced them by steady state heat loads. And we gave the assembly another about 15 hours to stabilize. And that's what we use for the correlation. Now, anyone who's ever done a thermal model correlation using this data knows that this can be a very painful exercise, especially in complete systems like this. You have a complex thermal model with dozens of thermal couplings, heat paths in series and parallel. You can spend a lot of time trying to balance out the different values, and there's not one unique solution to this problem. So for this project, what we did is we decided to take another route, which we thought would be easier. We have a software here available, which is called HEADS, which can do design space exploration and optimization, amongst other things. So what we did is we took our thermal model, we plugged it into the software, and we defined what the variable parameters were. Based on the test observations and experience, what the parameters we thought could vary and impact the temperatures. We took the thermocouple temperatures and set them as an objective. The optimization, we press play, and voila, the software did a lot of the work for us. Now, this is not a perfect world, not a perfect solution. At one point, this optimization plateaued and we still had to do some manual work. The reason for that is because there are always going to be deviations between a thermal model developed for analysis in space and a test performed on the Earth. Give you a few examples on top of my head. For example, the MLI efficiency will not be the same on the Earth as in space, obviously, because of gravity. You know, some blankets, horizontal blankets will sag and it will have a negative impact on their activity, whereas the vertical blankets will be pretty good. In this case, since we had a number of test heaters, it also had an impact on the emissivity on some of the surfaces. And these are the surfaces with a lot of power dissipation, so it does have an impact on the temperatures. And all of these heaters had to be powered with harnesses rooted within the system. These harnesses were not present in the thermal model and they could create some heat leaks. So to account for all of that, we're just using a DEC software was not enough. We still needed an engineering touch and some manual tuning to achieve a proper precision. In the end, we managed to correlate the temperatures for that cold case within a few degrees, about between 4 and 5 degrees. We could not achieve a perfect correlation, mainly because 4 days in a cryogenic radiative environment with minimum dissipations is not nearly long enough to reach steady state temperatures. In fact, 14 days is hardly enough. And since we were doing a steady state correlation, for what we did is for some of the heavier components, like the bigger radiators on the outside and the handling plate under the setup, we had to look at the temperature curves and try to project the temperatures and determine what they would be like once the system had fully settled. So considering all of that, we were pretty satisfied with the precision of a few degrees in this case. After the cold case correlation, we also correlated a hot case, a hot plateau. And for that, we took a temperature set which was representative of lunar day operation with maximum internal dissipations and solar loading as well. So the heaters and the radiators were active to represent the solar radiation. Now, I should say this is a perfect test case for correlation, much easier to correlate than a cold case because there are big temperature gradients every. That said, you can see on the graph that's shown here that once again the temperatures did not have time to fully settle, but beggars can be choosers, so we made do with what we had. Since at this point we had the correlated values from the first set of data, the gold case, this correlation went much faster. There's just one thing that baffled us here for a little bit of time. It's the MLI efficiency. Speaking fast, so I have enough time to discuss about this. The cold case was driven in big part by the conduction in the system. So changing the MLI efficiency by 0.02 or 0.03 didn't have much of an impact on temperatures. For the hot case, the radiative environment was still very cold. So the TVAC shroud was still flooded with LN2. But we noticed that if we increase the effectivity of the MLI, the internal structure would cool down instead of warming up. And that's the opposite of what you would expect. But after some playing around with the model, we figured out that This is because most of the solar heat loads were applied on one single radiator on the plus Z side, so about 475 watts out of the 750 watts in the system. And well, apparently some of that heat was making it into the main body of the rover by radiation, not only through conduction through the mounting points. So in this case, increasing the efficiency of the MLI at that location meant that less heat was making it from the radiator to the internal structure. So it was a pretty interesting thermal observation here. In the end, after tuning the model, we managed to get a very good correlation here with most of the temperatures being within a degree or two of this data. Now, as I mentioned a couple of slides back, the main objective of this correlation exercise was to verify that the heater power was sufficient over the full lunar night. At this point, what we had done is to correlate one set of data which corresponds to normal lunar daytime operation and another set which corresponds to lunar night survival. So all that was left to do is to close the gap by doing a transient simulation over the full 14 days lunar night. For that, we used the temperatures from the hot plateau as an initial condition. For the couplings which have a temperature dependency, we used linearly interpolated temperature-dependent values. I should mention at this point that although there are variations, they're pretty small, so the linear interpolation seems like it was accurate enough for this purpose. For the LHPs, we used the correlated values from the cold and hot plateaus, and we assumed the transition temperatures to be as per the datasheet. So here you can see a graph just below that shows you the temperatures of a few unnamed components over the full night. So this gives us a couple of very interesting observations. First, the cool down time before the initial heater click-on, which was about 1 day. This is almost identical to what we observed during the test. So gives us confidence. It's a good thing. The heater duty cycle over a full night was also the same one as we observed in the test. The graph here shows us that the temperatures had not fully settled after 4 days, which is once again what you observed during the test. But one very important observation here is that the temperatures had almost fully settled after 14 days. And I say this is an important observation because what we're assuming in the simulation is that we're operating at full maximum capacity with maximum solar loading up until sunset. And then at sunset, everything drops down to 0 instantaneously, which is not realistic. The reality won't be like that, of course. In reality, the initial temperatures will be colder than what we had here. And seeing that we had almost reached steady state after 14 days tells us that the initial temperatures wouldn't have much of an impact on the final temperatures, which is a good thing. So, all in all, seeing as the simulation results we obtained are in good agreement with the test observation, we're pretty confident in the values we obtained in the test and in the simulation. So, in conclusion, for this project, we did several things. For the correlation activity, we tried using a DSC software to try and solve the thermal balance. But it worked pretty well to get a rough order of magnitude for the values, but we still had to do some manual tuning to account for the testing ponderables as I discussed before. The precision was limited by the number of thermocouples. This is not news to anyone, I guess. If you have 2 thermal resistances in series and only 1 thermocouple at each end, well, you can only correlate the sum of the 2 resistances. You can't correlate each one individually. That said, we fully understand that having hundreds of thermocouples is not really practical. And also the harnessing of all these thermocouples would probably have a negative impact on the behavior, the thermal behavior during the test. So the number of TECs and the durations allowed us to reach a precision that was sufficient with regard to the test objective here, which was to correlate the heater power over the lunar night. In terms of the thermal design, we're pretty happy about the results here because we've managed to successfully demonstrate that new LHP technology works as intended. The performance of the system as a whole was better than we had initially expected. We had a second heater which never clicked on because the local temperature never got cold enough. So that's a good thing for us, less power consumption for insulation. And at the end, we managed to confirm that it's feasible with our thermal design to survive during the night without a radioactive heat unit. Was the main objective of this project here. So this already concludes my presentation. Did anyone have questions?
Thank you, Jean-Francois, for your presentation. Warren, do we have any questions from the chat?
Yeah, we do. A few questions. So first one, what resources do you recommend for new engineers to consult in order to learn more about model test correlation?
That's a very good question. Most of my learning was done through experience, through trial and error. If you send me the questions, just send me an email. You can find my address in the paper, and I'll try to find some good resources for you.
Okay, great. The next question, and perhaps she missed this, but what software did you use for the correlation?
For the thermal model itself, we used SimCenter 3D, the Space System Thermal Module. And for the correlation, we used a software called HEEDS, H-E-E-D-S, which was that Design Space Exploration software was talking about.
Okay, and final question, are there any presentations or papers about the type of LHPs you used that you would recommend?
You can look up I can't share too many technical information here, but you can look up the company I mentioned, Alatherm. They're the ones for developing that LHP, so they'll be happy to help you and give you guidance if you need their products.
Okay, and another question just came through. So the audio for this person cut out, but you said something along the lines of horizontal radiators were more effective than vertical ones, and he's asking for clarification on that statement.
Oh, yeah, it did cut off. Obviously, I was talking about MLI with gravity radiators because of the sag created by gravity on the blankets.
Okay, thank you.